today's video, we will be talking about the binomial theorem. Now, if you open the IB Math AA guide and scroll all the way to page 32, you will see that the binomial theorem is covered under SL 1.9 as well as under AHL 1.10, the HL extension of the theorem. Now, to be able to get into the binomial theorem, you have to know how to use the Pascal triangle and the NCR notation. I've covered the Pascal triangle in a separate video, which I highly recommend for you to watch before starting this one. First of all, what do we mean by the binomial theorem? So the prefix bi means two. And so the binomial theorem is about expanding the addition of two terms to the power of n. So a and b can be any numbers, they could include x's, and n can either be an integer, which is what the SL students are responsible for, or it could also be a rational number, which is the HL part of the program, which we will get into in another video. So for now, just think of n as a positive integer. Now, let's start with the basics. So what if we want to expand a plus b to the power of 0? Now, you should know that anything to the power of 0 is equal to 1. Now, what about a plus b to the power of 1? That is just a plus b. Now, a plus b squared, and I'm sure you're familiar with this formula, so it's a squared plus 2ab plus b squared. If you're not, just multiply a plus b by itself. And if you order the terms that you get in descending powers of a, starting from a squared, this is exactly what you will get. Now, I invite you to pause the video and do the same thing for a plus b cubed. Again, arranging in descending powers of a, we get a cubed plus 3a squared b plus 3b squared a plus b cubed. Now what I'm going to do now is just write the coefficients of a and b in red. So whenever there's no coefficient, that means there is a 1. Now, do these numbers look in any way familiar to you? They should. These are the coefficients of the Pascal triangle. It's very fascinating how this triangle, which as we saw in the other video is a very easy triangle to build, somehow gives us the coefficient of the binomial expansion. Now, let's make some observations about the terms that we get. The first thing that I want you to think about is how many terms we get for each expansion. Now, for n is equal to 0, we get 1 term. For n is equal to 1, we get 2 terms. For n is equal to 2, we get 3 terms. So let's generalize. So for a plus b to the power of n, we will end up having n plus 1 terms. Now the other thing we can notice is how these terms are constructed. Now if we look for instance at the line with n to the power of 3, whenever there's no power of b, I want you to think of having b to the power of 0. So I'm just going to write this. So we have Pascal triangle coefficients. And then looking at the first term, we have a to the power of 3, and then the second term a to the power of 2, the third term a to the power of 1, and then a to the power of 0, which kind of makes sense because we actually ordered them in descending powers of a. Now look what happens with b. It's actually the exact opposite. We have b to the power of 0, b to the power of 1, b to the power of 2, and finally b to the power of 3. So moving in one direction, the powers of a keep decreasing while the powers of b start increasing. Now another thing I want you to note is the sum of the powers. So 3 plus 0 is equal to 3. 2 plus 1, which is the power of b here, is equal to also 3. 2 plus 1, again, equal to 3, and then 3 plus 0 is equal to 3. And that is true for the previous rows as well. Here we have 2 plus 0, which is 2. 1 plus 1, the two powers of a and b, equals to 2, and then b to the power of 2. The sum of the powers of each term are always equal to n, and you can see this for n equals 1 as well. Now with these observations, we can actually now write down the expansion for a plus b to the power of anything above 3. So if we take a plus b to the power of 4, for example, what I like to do is I like to first start with the powers of a So starting from a to the power of 4 and then decreasing it by 1 each time. So you see, I've left some spaces here because as we saw earlier, every term is made up with 3 components. So we've just filled the a part of it. And now we start filling the b. So here we have b to the power of 0, which you don't actually have to write because it's 1. B to the power of 1, b to the power of 2, b to the power of 3, and finally b to the power of 4. Now we're not done yet. Remember, we still have to add the Pascal triangle coefficient. Now, if you look at the row n equals 4, you can add the coefficients now. So the first coefficient is 1, as always, and then 4, 6, 4, and then 1. Now, you can do the exact same thing for a plus b to the power of 5, 6, 7, whichever value you want. So now instead of writing the expansion with the actual values of the coefficients, I'm going to rewrite this expression. Now, instead of having the coefficients 1, 4, 6, 4, 1 appear as they are, I'm going to write the NR notation, which we saw in the previous video. So the 1 here belongs to the row n equals 4 and has r equals to 0. So 4, 0. And then the 4 here is the second one, which has r equals to 1. And then the 6 has n equals 4. Obviously, all of these coefficients are on the row n equals to 4, so all of them will have the same value for n, and it's just the r value that keeps changing. So here 4, 2, which gives us 6, and then 4, 3, which gives us 4, and then 4, 4, which gives us 1. Now the reason why I wrote it in this way is because now we can draw a lot more conclusions about the relationship between the Pascal triangle coefficient and the powers of a and b. The first thing you might notice is that the power of b is always equal to the value of r. 1, 1, 2, 2, 3, 3, and so on. And as we said earlier, the sum of the powers is always equal to n. So in this case, 4. So here, since we've put 0 here, then what's left is 4. Since we already have a power of 1 here, what's left is 3. Here we have 2, then what's left in 2, and so on. So putting all these observations together, we can now write down what we call the general term, which basically is a general expression that describes all of these terms in any binomial expansion. So as we saw, the first part of any term in a binomial expansion is a coefficient nr, followed by a power of a and then a power of b. Now I've put x and y, but actually we can represent the powers of a and b in terms of n and r. As we said, the power of b is actually always equal to r. The power of a has to be whatever is left of n, such that when we add the two powers, we get n back. So that is actually just n minus r. And this is actually the formula for all of the terms that we've seen earlier. All we gotta do is start from r equals 0 and keep increasing by 1, and then we will end up getting all the terms in the expansion. And notice how, because we start with r equals to 0 and we go all the way up to n, we end up with n plus 1 terms and not just n terms. Now we will see why the general term is very useful. In many IB exercises, they will ask you to find a specific term in an expansion. Now one way of doing it is to actually expand the whole thing and try to find the particular term that they're asking about, which obviously takes a lot of time. The other way is to use the formula for the general term and directly find the term that we're interested in, which I will be showing you later. Now, if you're an observer, you might ask me this. Isn't a plus b to the power of 4 the same thing as b plus a to the power of 4? We can swap the order of a and b and we should be able to get the same thing. And that is in fact true. Now, the way we've expanded this is that we've ordered the terms with descending powers of a. Now notice if we had decided to order the other way around with descending powers of b, so that term here would have been our first term, wouldn't it? Now, would that give the same thing? And the answer is yes. And that is because of the symmetric property of the Pascal triangle. So 4, 4 is actually the exact same thing as 4, 0. 4(3) is exactly the same thing as 4(1). So it doesn't really matter which term you decide to take as your A and which term you decide to take as your B. That means that this formula can actually be written like this. That would still give you the exact same expansion. Now, for the sake of simplicity, I would just stick with one form and work with it throughout. And now let's start with some exercises. So in this exercise, we're asked to consider the expansion of x plus 2 to the power of 11. Now, the first question is very straightforward. Write down the number of terms in this expansion. As we have seen, we always end up with n plus 1 terms, which means 11 plus 1, so we'll end up with 12 terms in total. Now, the second question is about finding the term containing x squared. Now, as I said before, the long way of doing this is to actually just expand the full expression and then find the term x squared. Now, that is not very efficient, so let's see how we can use the general formula to find the term right away. So I advise you to always start by writing the general term and filling out what you know and leaving out what you don't know. So the general term is 11r. Again, r is the variable that fluctuates from 0 all the way up to n. So in this case, 11, giving us all the different terms of the expansion. And then we have x, which is our a here, to the power of 11 minus r, times 2, which is our b here, to the power of r. Now, very simply, what is the term that we're interested in? We want the term x squared. And so you look at the power of x and say, okay, what is the value that will set 11 minus r to 2? So basically we solve 11 minus r is equal to 2, and we get that r should be equal to 9. And once we have the r value, it's very simple. We just substitute that into the general term. And so we get 11, 9, x to the power of 11 minus 9, which is 2, as requested, and then 2 to the power of 9. And now we can simplify. This exercise can come as a paper 1 or a paper 2. So if it does come as a paper 2, then you can just compute these values using your calculator. If it's a paper 1, then you can compute it manually using the NCR formula as follows. Now, if you don't know how to do that, then I advise you to go and watch the video about the Pascal triangle coefficients, which clearly explains how to compute this using the formula. Now, the process is quite simple. We start from the denominator and we write out the factorial of r, which is 9. And then we move on to the top and we start writing the factorial of our n, which is 11, up until we reach the exact same number of terms top and bottom. And once we reach that stage, you will see that there's a lot of simplification we can do. 3 and 3, 4 and 4, 5 and 5, and so on. And so we're left with 11 times 10 in the numerator, and then 2 times 1, which is just 2, and then we can simplify even further, the 10 with 2, and we get 55. And so 11, 9 is equal to 55. So that is equal to 55, and I'm going to leave out the x at the end, and I'm going to start with 2. So 2 to the power of 9. Now, if you don't know your powers of 2, I would advise you to learn them up until 2 to the power of 10 at least. It comes in very handy sometimes. Now, if you don't, 2 to the power of 9 is 512. And then we write our x squared. So what are they asking us here? Find the term containing x squared. So all we got to do is just multiply 55 by 512, which gives us 28,160 x squared. Now, in general, the IB wouldn't give you such big numbers on paper 1. So I would say this is more likely a paper 2 type of question. But in any way, the process is still the same. You start with the general term, you solve for your r to find the specific term that you're interested in, and then you substitute that value of r into the general term, and it's just a matter of calculation. Now, this example was actually quite simple because here the x appeared in only one term and it appeared to the power of 1. Now, we're going to see other examples where that is not the case. Now, let's take a look at this exercise. So the first part asks us to expand these two expressions. So let's start with the first one. So we have x minus 1 over x all to the power of 3. So as I said before, in some exercises, the x doesn't only appear in A or just B, it appears in both A and B. Now let's expand. So we know that we first start with the Pascal triangle coefficient 3, 0, and then we have our first term x to the power of n, which is 3, plus 3, 1, which is the second coefficient in the Pascal triangle, x to the power of 2. And now be careful, this is not 1 over x, this is minus 1 over x. So make sure to include the minus with you. Plus 3, 2, x to the power of 1, which is simply just x. And then we have minus 1 over x squared. And then finally, the last term, 3, 3, x to the power of 0, which is just 1, so we don't have to write it. And then minus 1 over x to the power of 3. And now let's simplify. So we know that 3, 0 is 1, so that just leaves us with x cubed. 3, 1 is 3, so that's 3. And then here we have x squared times minus 1 over x. So we have a minus, which will turn this plus into a minus. And then we have x squared over x, which is just x. And then plus 3, 2 is 3. And here we have x times minus 1 over x squared. Now the square will cancel this minus because it's an even power. And so we're left with x over x squared, which means we're going to have x at the denominator. And then 3, 3, which is just 1, and then minus 1 over x cubed. Now, the minus stays because that's an odd power, so we have minus 1 over x cubed. And we are done. Now, if you are unsure about the simplifications that I did here, take your time, do the exercise on your own, and you will see that this is exactly what you will get. Now let's do the same thing for the second one, which is the exact same expression to the power of 4. Again, we have 4, 0, x to the power of 4, plus 4, 1, x to the power of 3, minus 1 over x to the power of 1, plus 4, 2, x squared minus 1 over x to the power of 2. Now, every time you can stop and check with yourself if the powers add up to 4. That's a good way to make sure that you haven't missed out any terms. And then we have 4, 3, x to the power of 1, minus 1 over x to the power of 3. Finally, 4, 4. The x is to the power of 0, so we don't have to write it. And then minus 1 over x to the power of 4. So I would suggest that you pause the video here, do your own simplification, and come back to check if we got the same thing. Now, you should get x to the power of 4 minus 4, and then the x powers, so we have x to the power of 3 at the top and x at the bottom, so we're left with x squared. And notice how the plus turned into a minus because we have a minus here. And then plus 4, 2 is 6. And then we have x squared at the top, x squared at the bottom, and the minus turns into plus because it's to an even power. So it's just plus 6. 4, 3 is 4. And now again, we have a minus to the power of 3. So actually that plus will turn into a minus. And we have an x at the top and an x cubed at the bottom. So that gives us x squared at the bottom. Finally, we have plus. The reason why it's a plus is because it's minus 1 to the power of 4, which is 1. And then we have 1 over x to the power of 4. Now, this was all good and easy because these two values of n are not that big, so we didn't end up with that many terms. But if you look at the second part of the question, it asks us to find particular terms in the expansion where n is equal to 10. Now, that's going to give us 11 terms, and it's not going to be very nice to write it all down. Instead of writing down the full expansion, we can use the general term formula to find the exact term that we're interested in. So let's write down the expansion that we want, x minus 1 over x to the power of 10. Now, as we did earlier, all we got to do is just write down the general term. Our n is 10, our r is the one that we don't know, and then we have x to the power of 10 minus r, and then minus 1 over x to the power of r. Now, when we used the general term earlier, it was very straightforward because we only had one x term. Now we have two. So when these terms get simplified, like we've seen earlier, with n equals 3 and n equals 4, the x powers get combined together and then they simplify. And so if they're asking us for a particular power of x, we actually have to combine these x's. So we just have one x with a combined power. So let's do that. So the 10r, we leave it as it is. X to the power of 10 minus r. And then here, be careful. This is a minus 1. So it's minus 1 to the power of r. And then we have x to the power of r at the bottom. So I just expanded the power of r over the numerator and the denominator. And now we can combine the powers of x together. So here we're going to use the rule a to the power of n over a to the power of m is equal to a to the power of n minus m. So basically we're going to subtract the power of the bottom from the top. So we get 10r x to the power of 10 minus r minus r. So that's going to give us 10 minus 2r. And then finally, minus 1 to the power of r. Now, once we have the general term simplified, we can answer all of these three questions. So the first question is asking us to find the constant term. Now, what do they mean by the constant term? The term constant means it doesn't change. It's not a variable. And as you know, x is a variable. So whenever they ask you to find the constant term, that means they want the term where the power of x is equal to 0, because that will just give you 1, which means you actually won't have an x in that term. And so for part I, we want 10 minus 2r to be equal to 0. And if we solve for that, we get that 10 is equal to 2r, which means r has to be equal to 5. And once you have the r value, you just plug it in. So we get 10, 5, x to the power of 10 minus 2 times 5 is 0, which is exactly what we wanted, and then minus 1 to the power of 5. And now we simplify. Now this is a calculator question, so you can go and use your calculator to find the value of 10, 5. And you will find that it is equal to 252. And then x to the power of 0 is just 1, so we don't have to write anything. And then minus 1 to the power of 5, that's an odd power, so that gives us minus 1. And so the answer is minus 252. That is our constant term, so the term that doesn't have any x's in it. And now let's do the same thing for the term in x squared. So we don't need to redo the work that we did earlier. We can use the exact same combined power of x, 10 minus 2r, and we set it to 2. And that gives us 8 is equal to 2r, which means r is equal to 4. And we substitute that into our general term. We get 10, 4, x to the power of, so 10 minus 2 times 4, that will give us 2. Again, it's worth checking that the value of r that you found is the one that gives you the correct power of x that they want. And then we have minus 1 to the power of 4. Minus 1 to the power of 4 is just 1. And then again, you can use your calculator to find what 10, 4 is. And you will find that it's equal to 210. That is the term that they're interested in. Now, I want you to pause the video and attempt the third exercise on your own. So now we want the power of x to be negative 2. I hope you've attempted it. Let's see what we're going to get. So again, the combined power of x is 10 minus 2r, and we set it to our desired value, which is minus 2. And now we solve, we get 12 is equal to 2r, which means r is equal to 6. And we plug in this value into our general term. So x, so let's just look at what the general term said. So x to the power of 10 minus 2 times 6, so 10 minus 12, which in fact gives us minus 2. Again, it's worth checking. And then we have minus 1 to the power of 6. Again, this is an even power, and so the minus 1 to the power of 6 will just be 1. And now grab your calculator and compute 10, 6. You will find that it's also equal to 210, and again that has to do with the symmetry of the Pascal triangle. So 10, 6 and 10, 4 are exactly symmetric about the center, which is 10, 5. And now let's take a look at a less direct question which are generally the type of questions that you will get in your exam. Now it says, consider the expansion of 3x squared minus k over x to the power of 9, where k is a positive number. The coefficient of the term x to the power of 6 is 6048. Find the value of k. Now, instead of having the value of a and b and finding the value of a specific term, we are actually given the coefficient of that term and we're asked to find the value of k. Good news is all you need to do is use the general term as we did before. So again, let's write this down. So we have 9r. Now again, we don't know which value of r will give us the combined power of 6 at the end, so we leave the r as it is for now. And then we have 3x squared all to the power of 9 minus r times minus k over x to the power of r. And that is our general term. Now to find the term with x to the power of 6, we have to first combine all the powers of x together, which means we have to expand and simplify. So the 9r we leave as it is for now, and now let's open up these brackets. So we're going to get 3 to the power of 9 minus r, and then x squared all to the power of 9 minus r, minus k to the power of r over x to the power of r. So we get 9r, 3 to the power of 9 minus r, and now we expand these brackets. And here we're going to use the rule a to the power of n all to the power of m is equal to a to the power of n times m. We're going to multiply the powers. And so we get x to the power of 18 minus 2r. And then we get minus k to the power of r over x to the power of k. And now we combine all the x's together. So we can write everything else as it is. And we get x to the power of 18 minus 2r minus r, and that gives us 18 minus 3r minus k to the power of r. Now we can find the required value of r that will give us the power 6. And so we solve. 18 minus 3r is equal to 6. That means that 12 is equal to 3r, and that means that r is equal to 4. So that is the value of r that will give us the term that we want. And now we just plug it back in. 9, 4, 3 to the power of 9 minus 4, that is to the power of 5, x to the power of 18 minus 3 times 4, that's 18 minus 12, which gives us 6 as required, and then minus k to the power of 4. Now, 9, 4 is 126. Again, you can use your calculator to find these values. Then 3 to the power of 5 is 243. And then I'll leave out the x at the end. We have minus k to the power of 4. Again, we have an even power, so the minus will turn into a plus, and we're left with k to the power of 4, and then x to the power of 6. And now we multiply these two, and we get 30,618 k to the power of 4, x to the power of 6. We are told that the coefficient of the term in x to the power of 6 is equal to 6,048. And the coefficient is this part here. So all we got to do is set this equal to 6,048 and then just solve for k. So we get 30,618 k to the power of 4 is equal to 6,048. That means that k to the power of 4 is equal to 6,048 divided by 30,618, and that gives us 16 over 81. And now all we got to do is just take the fourth root of that value to find k. And you don't even need the calculator for that. You should know that 16 is 2 to the power of 4 and 81 is 3 to the power of 4. So that just gives us 2 over 3. And notice here I didn't put plus or minus because we are told that k is positive. Otherwise, you would have to given both answers plus 2 over 3 and minus 2 over 3. So in this video, we have seen how to use the Pascal triangle coefficient to expand a plus b to the power of n. We have seen how we can find a specific term of interest with a specific power of x. So this covers all the theory of the SL part of the binomial theorem. Now, if you have any question or if something wasn't 100% clear to you, or if you have a very hard exercise that you still can't do on your own, write me a comment and I will try to make another video to answer your questions. I hope you found this very useful, and if you have, please subscribe to this channel to get more videos to help you prepare for your IB exams. Now, if you're an HL student, rest assured, I will be covering the HL extension of the binomial theorem in a separate video. Also, I want to remind all of you that I offer one-on-one private tutoring and that you can book a 30-minute free trial session on ibmathsupport.com. See you in the next video.